come to the CSP seminar this week. For this week, we're very happy to have our Michigan UMich alumni to come back and give us this very special talk. Zhongyu Li was the previous PhD in our departments, working with Professor Jeff Fissler, and on the computational imaging and also the AI methods for the inverse problem. And currently, as you can see in the slide, so his affiliation has been with the KLA. So he's currently an algorithm engineering in KLA and locally in Ann Arbor. And he is working on developing signal and image processing and machine learning methods for semiconductor inspection with an emphasis on the photomask defect detection. So from this talk, I think you will get an idea what Zhongyu is currently working on and what KLA is working on. And also it will be a good opportunity to get connected as well. Yeah, so Zhongyu, prepare to take your time.
Yeah. Okay, before I start, can anyone on Zoom hear me? Or see my screen?
Yes.
Or okay, thank you. Okay. Good afternoon, everyone, and thank you for joining. I'm Zongyu from KLA Corporation. Today, I will talk about how signal processing, image processing, and machine learning are used in reticle inspection. I want this talk to connect two perspectives at the same time. The semiconductor manufacturing context, which explain why the problem matters so much, and from the algorithm perspective, which explains why the problem is technically interesting. To make the rest of the talk easy to follow, here, let me start with the quick roadmap. So I will begin with why the reticle inspection matters, because the application context really determines the technical requirements. And then I will walk through the inspection pipeline itself, from reference generation to residual formulation and the final detection. And after that, I will discuss why machine learning is increasingly useful in this domain, especially under weak signal and limited data conditions. And finally, I will close with a few open research directions and some broader comments on why this area is exciting from a both research and career perspective. Yeah, with that roadmap in mind, let me start with why the reticle inspection matters. So this slide zooms out and places the reticle inspection inside the larger semiconductor manufacturing flow. So you can see from the overall ecosystem spans from the design. You can see some companies are working on that. From design to reticle making, wafer fabrication, lithography, and etching packaging, and finally test and shipment. You might see some big names like TSMC, Samsung. They are working on wafer fab equipment, or ASML. They have the EUV lithography tool, and the KLA's role across this flow is the process control and inspection, and it helps detect the defects and variation early enough such that they can be corrected before they become costly yield problems. And for today, I will focus one specific part of that broader mission, the reticle inspection, because this is a particularly clear example of how imaging physics, signal processing, and machine learning come together. There's also a even broader ecosystem around this, beyond just the wafers and reticles. So process control and inspection are not limited to the wafer fabrication or reticle manufacturing. They also connect to packaging, components, printed circuit boards, substrates, and the end markets that ultimately depend on the reliable semiconductor technology. So the key takeaway is that the advanced manufacturing depends on the visibility and the feedback at many levels. In other words, the inspection is not just a side activity, it is part of the control loop that keeps the entire system stable. A useful way that customers often describe this role is to call these tools the eyes of the fab. So in semiconductor manufacturing, many process steps repeat over and over. Deposition, lithography, etching, the CMP stands for chemical mechanical planarization, and so on and so forth. Because these steps are repeated, even small deviations can accumulate and eventually create major problems. That is why inspection and metrology tools are often described as the eyes of the fab. They provide the visibility needed to know whether the process is behaving as intended. The reticle inspection is especially important in this loop because it helps prevent the defects from propagating through repeated exposures in the lithography. To understand why the reticle inspection is so critical, let's define what a reticle actually is. A reticle is the patterned plate used as the master template in lithography. The pattern on the reticle is projected onto the wafer, typically with optical reduction. So the reticle effectively controls what gets printed onto the chip. Different reticle types, especially you see DUV and EUV reticles, they use different materials and physical principles. And those differences matter because they strongly influence how a defect gonna appear under different inspection modalities. One of the key ideas for the rest of this talk is that the defect visibility depends not only on the defect itself, but also on the interaction between the material system and the imaging system. Once we recognize the reticle is the master template, the yield impact becomes much easier to understand. So, deep ultraviolet. Yeah, DUV stand for deep ultraviolet, and the EUV stand for extreme ultraviolet. Yeah, yeah. So the heart of the issue is the role of the reticle as the master template. Um, because the same reticle is used repeatedly, a defect on the reticle is not a one-time error. It can replicate across many dies and many wafers. This is what makes the reticle inspection one of the highest leverage points in the semiconductor manufacturing for yield protection. Catching one defect early can prevent very large downstream loss. So this becomes concrete, even more concrete when we think in terms of the yield loss. A single reticle defect can create repeated printing errors across many exposures and many dies. So the cumulative impact can become very large very quickly. These defects can take different forms, such as soft defects such as particles or contamination, and pattern defects such as missing or bridged features or some phase-related errors in advanced reticles. But in all cases, the important point is the same. Inspection is not, it is about preventing systematic yield loss. It's not just identifying anomalies in isolation. Where and how we inspect depends strongly on the manufacturing setting. So let's distinguish two main operating environments. There are two major operating environments for the reticle inspection, and the requirements are not identical. So in the mask shop is after the reticle is designed and before the shipping of the reticle. The goal is to qualify the reticle before it is shipped. So the sensitivity is the top priority, and the die-to-database comparison is often central. I will explain die-to-database or these methodologies later in more detail. And in the fab is after they receive the reticle, they need to do requalification of the reticle such that they can be used in the lithography. The inspection happens during the production use where throughput become more critical, while still maintaining a near zero false escapes. So the same general detection problems exist in both settings, but the practical operating point, the balance among sensitivity, false nuisance, and the speed is different. Another key trade-off comes from not from the workflow, but from the imaging modality itself. So different inspection modalities sit at different points on the performance trade-off curve. The DUV, which stands for deep ultraviolet, it uses 193 nanometer wavelength. Um, it can provide a very high throughput, but at a relatively lower resolution. So you're gonna see the point spread function gonna blur out everything, but the image has lower noise compared to other modalities. The EUV can improve the resolution, but at a higher cost and a more moderate throughput. And if you use electron beam, you can go to a very small pixel size, but it offers the highest resolution, but it is much slower compared to the DUV or EUV inspection tools. So there's no single modality that simultaneously maximizes the speed, sensitivity, and the resolution. In practice, inspection system design is always about balancing these competing requirements. With the motivation established, let's move to the actual inspection pipeline. Yeah, yeah.
So why are there so many mirrors for the EUV system? Is that just a cartoon or is it really that complicated?
Oh, yeah, that's really complicated, I think. It's a fully reflective mirror. There's, yeah.
Uh,
Yeah, I think DUV is more transmitted, but EUV is fully reflective. Yeah. Yeah. Okay, so the inspection is tightly linked to the lithography physics. The resolution and depth of focus depends on the wavelength and the numerical aperture. And as feature sizes continue to shrink, the distinction between the real defects and the normal background variation become increasingly subtle. So this means the inspection tools must improve not only the optical resolution, but also signal processing sensitivity in order to keep pace with the manufacturing requirements. In other words, the detection challenge grows as the underlying patterns become smaller and more demanding. With that physical context in mind, here's the high-level inspection workflow. At a high level, the reticle inspection can be broken into four stages: the image acquisition, reference modeling, residual formation, and defect detection. This sounds simple in a diagram form, but each stage operates under severe constraints. There's an enormous image volume, and we have strict throughput requirements and the need for very high sensitivity with controlled nuisance. So the real technical challenge is not just the sequence of the blocks, but making each block work reliably under industrial conditions. To see why each block is hard, let's first think about the skill of the search problem. So the defect detection is fundamentally a rare event detection problem. A reticle may contain on the order of billions of pixels or maybe 10 billions of pixels. Well, the number of the true defects may be zero or only a handful. So the signal of interest is extremely sparse. The detector must therefore search an enormous space. In other words, we are searching for extremely rare events under very tight operational constraints. Um, yeah. So another thing is we cannot miss a single defect. So this is like a fraud detection. You need to catch up all the frauds, but you cannot like have so many false alarms. And 100% recall is not optional. It is mandatory for the reticle inspection. Yeah. One of the major algorithm in this setting is how to construct the reference. The reference image is a defect-free image. This is a more detailed explanation of one of the previous slide I showed before. There are two main paradigms for reference modeling. There's a die-to-die comparison and the die-to-database comparison. Die-to-die compares image regions from different dies directly. So it is purely image-based. It is relatively simpler and is very fast, but it is struggle with systematic repeaters and some unique structures. And also, if you just have two dies, you can't say which die has a defect, right? And the die-to-database comparison, it renders a reference from the design data. The design data may be from like a CAD design or say some abstract lines. The die-to-database inspection can improve the coverage and allows the inspection of some unique patterns, but it depends on the accurate modeling and higher compute cost. So the trade-off here is essentially simplicity and speed versus a broader coverage and a stronger model dependence. The comparison becomes more intuitive when we look at them visually. So these images are generated by the AIs, are not actual images. Okay. Yeah. So there's no concern. So this slide gives an intuition behind the two reference strategies. In die-to-die, we compare two scanned image regions and ask whether they match. And in die-to-database comparison inspection, we compare a scanned image versus a rendered reference derived from the design data. So in both cases, the subtraction is supposed to reveal the unexpected structure, but the nuisance behavior is different depending on how the reference was created. That difference becomes more important later when we think about residual statistics and false alarms. Of course, the subtraction only works well if the alignment is extremely accurate. So if the test image and the reference image are even slightly misregistered, the strong pattern edges can produce large residuals that look very similar to the true defects. This is why registration often combines a core stage such as cross-correlation with a finer subpixel refinement stage. At a advanced manufacturing nodes, even a small fraction of the pixel matters. So registration accuracy is not just a helpful pre-processing step. It is a requirement for the entire pipeline to function correctly. Once the alignment is sufficiently accurate, you can form the residual and look for unexpected signal. The residual formulation is very simple. It's just subtract the reference from the test image. It is conceptually simple, but practically difficult. After alignment, ideally, when we do the subtraction, the result would only contain the true defect signal. But in reality, the residual also contains systematic artifacts such as edge displacement, non-uniformity, and short noise. So the real goal of this stage is to maximize the signal-to-noise ratio of the true defects while suppressing the nuisance components that survive the subtraction. To handle that residual property, we need to understand the noise sources inside it. There are several different noise mechanisms contribute to the residual. Short noise is one. It's a signal dependent and often modeled as Poisson distribution. There's also a quantization error. It adds a smaller floor, and the model mismatch introduced a structured, more pattern-dependent residuals. In many cases, a Gaussian approximation remains useful for detector design, but the real system also experienced the run-to-run variation, which makes the statistics non-stationary. That non-stationarity is important because it breaks many idealized assumptions that classical detectors would otherwise rely on. So one classical solution to spatially varying noise is to normalize locally rather than doing a threshold globally. The value of this is that the raw residual magnitude is not directly comparable across different pattern contexts or illumination conditions. Without normalization, a single global threshold tends to overfire in noisy regions and miss weak but important defects in the quieter regions. By normalizing locally, the detector can create a more uniform detection landscape and makes the threshold selection much more stable. After thresholding, you still need to convert the pixel level responses into the object level candidates. So this is how the morphological operations are useful. Some these operations including erosion, dilation to clean up the binary response. And then we can do connected component analysis that turns the pixel level detections into object level candidates. So features such as area, parameters, peak intensity, bounding boxes, and aspect ratio can then be used to filter the nuisance and produce a more meaningful candidate list for a downstream review. So far, this has been a classical defect detection pipeline, and now let's move to machine learning. But why we should do machine learning? This in many settings, the classical rules become harder and harder to twin and less robust when the signal is weak and the nuisance is structured. So this is why machine learning has become more increasingly attractive in this domain. So let's start by asking why the classical approaches begin to struggle. Like I mentioned before, there are a lot of limitations to the classical methods, such as Poisson noise, correlated variation, low contrast defects, and combined recipe tuning all make the handcrafted detection increasingly difficult. And machine learning is more attractive because the neural network can learn more hierarchical noise-aware features and combine local detail with a broader context rather than just relying on some manually specified thresholds and rules. One practical example is to use a lightweight neural network that is designed with deployment in mind. So this slide give some neural network example. Again, this is a toy example. It's not review anything that is in the production. The challenge is that the signal varies because of the shot noise, material contrast changes, and stochastic variation, and aliasing-like effects, which all make rule-based separation harder. And a lightweight convolutional neural network can learn features that are more invariant to these nuisance, while still remaining sensitive to the weak defects. If that network can be quantized and deployed efficiently, it becomes more useful not only in research but in actual inspection systems. So a related direction is to ask whether a modern neural network architecture can offer additional benefits. There's one interesting architecture is called ConNext because it keeps both the basic convolutional structure while incorporating more architectural choices. That makes deployment easier than some attention-based alternatives, especially when deterministic behavior and straightforward 8-bit integer quantization matter. So in industrial inspection, these properties are often nearly as important as a raw benchmark accuracy. So this slide is really about how the deployment-friendly characteristics of the architecture, not just its representational power. Of course, even a strong model architecture has to satisfy the real system constraints. In industry, the best model on the paper is not always the best model in the system. There's a throughput, latency, model size, reproducibility, qualification effort, and data scarcity all constrain what can actually be deployed. That means the real optimization problem is not simply maximizing the accuracy. It is balancing accuracy with robustness, validation cost, and compute budget. So in practice, the deployment is a full system design problem. It's not just a modeling problem. And one of the strongest constraints behind all of this is the data problem. Data is one of the biggest bottlenecks in inspection machine learning. Real defects are rare, and customers' data is proprietary. And the visual distribution shifts across new chip designs and operating conditions. So we often face the label scarcity, the domain shift, and the restricted data sharing all at the same time. That's why evaluation methodology, some adaptation strategy, and synthetic data generation become important for the machine learning story rather than those secondary details. If the labels are scarce, then the next question is how to evaluate the models responsibly in that regime. When the class imbalance is extreme, the standard evaluation may be very misleading. Like the accuracy is almost meaningless here because a trivial classifier can still look excellent numerically. More useful metrics include precision recall behaviors, F-beta scores that can emphasize recall, and capture rate under a fixed nuisance budget. The training also has to adapt through oversampling, focal loss, and hard negative mining, while evaluation must avoid leakage across correlated radicals or radical types. Yeah. After covering the topics for current radical manufacturing, let me step back and look at a few open research directions. A major practical challenge is that every new chip design introduces new pattern statistics. So a model trained on the one radical type or design may underperform on another, even if the underlying detection problem is conceptually similar. There's possible solutions, including like limited label fine-tuning, distribution alignment methods such as the maximum mean discrepancy or some adversarial adaptation, and self-training with pseudo labels. But the deeper question is how to benchmark these methods rigorously when the data often cannot be shared across sites. If the labels remain scarce under that shift, then an obvious next question is whether we can learn more effectively without them. So that's why unlabeled training becomes very attractive. Like self-supervised learning, mask autoencoders, and domain-specific foundation models can help learn useful representations before large label datasets are available. Like synthetic data generation, whether it's a physics-based or GAN-based or diffusion-based, may also help increase the training diversity. But the key validation criteria is not simply whether the generated samples looks realistic. It is whether they improve the downstream detection performance on the real data. Yeah. Another promising direction is to use physics itself as part of the learning prior. One powerful idea is to embed the known optics or image formation physics directly into the learning process. So the network is encouraged to produce solutions that are consistent with both data and physics. This can improve generalization and reduce dependence on the large label datasets. This is especially attractive in semiconductor inspection because the underlying physics can often transfers even when the customer data itself cannot be shared. For anyone who wants to explore these ideas further, here are some useful references. And starting from this slide, I will shift from the technical content to a broader environment around this work. Yeah, there are several great reasons to join us. The first reason is simply the scientific depth of the problems. The problems sit at the intersection of optics, sensors, signal processing, machine learning, and manufacturing. And many of them are generally hard enough that takes years rather than weeks to solve well. For people who enjoy interdisciplinary technical challenges, that combination makes the work especially rewarding. The second reason is that solving these kind of problems require a long-term investment in innovation. This creates room for both intermediate engineering impact and the longer horizon exploration of new methods and ideas. In practice, that means the environment supports not only building systems that work today, but also improving the technology foundation for the future. Another defining feature of this work is how multidisciplinary it is. The progress in the field rarely happens with a single discipline. Real advances usually come from collaboration across hardware, software, optics, algorithms, data science, and production teams. That mix of expertise is part of what makes the field dynamics and intellectually rich. It is also a great environment for learning because the problem forces you to connect ideas across domains rather than staying inside one narrow specialty. And beyond the internal collaboration, partnership across the broader ecosystem matters as well. Semiconductor innovation is inherently collaborative. The manufacturing ecosystem is deeply interconnected. So major improvements often come from combining expertise across teams, organizations, and technology areas. And finally, there's a broader motivation behind all of this work. So even though this work can look highly specialized, its impact is broad. Semiconductor technology supports many of the systems that shape modern society, from computing to communication to mobility and AI. Improving manufacturing quality helps enable these broader advances by making the underlying technology more stable and scalable. So while the reticle inspection I talked about today is a very specialized technical field, its downstream impact extends much further. With that, let me close and thank you for your attention. I will be happy to any question.
Thank you, Zhongyu, for being patient from the audience. I have one, I want to learn more about if this is possible. That you mentioned about the business priors in the in your work. I wonder the business prior is applied in how you generate the data. For example, I say you want to have some neural network to reproduce which can constrain or satisfy the Maxwell equation. So you want to use that as the way to guide your data generation through the GAN, diffusion, or what else, or you want to use that as a tool to detect the abnormal artifacts.
I think the physics prior is both useful for you mentioned synthetic data generation as well as in the defect detection pipeline. If we can model the physics more accurately, then there's less artifacts that the network can there's less efforts for the neural network to distinguish or to filter out.
You mean in the downstream task detection?
It's you're gonna relax some challenging task that can be handled by that can be very challenging for the neural network to learn, but it can be modeled by the physics.
I see. Got it. Yeah, and also yeah, I'm not sure if like all these kind of models has been, trained or maybe developed like using the data you have to see how it can work, or maybe there's some like the ongoing project that is trying to explore what kind of the solutions or what kind of technologies can work better in this specific domain application.
You mean the data? What?
Yeah, I'm not sure like for this idea either the generative modeling or like the face informed, prior. So are this some like the idea?
We are working on that. And like I said, the semiconductors takes time to get something mature. So if we release something that is not mature enough, it's gonna create a lot of issues and gonna have millions of dollars of loss. So yeah, it takes time for things to get mature, to get really deployed in the field.
I see.
Yeah.
And even though there are some like the self-supervised representation learning approach, but generally speaking, at the end of the day, you still need the label data for the validation or the evaluation, right?
Right.
So in that case, so I wonder like what kind of the label data that you think that will be the most critical or the criteria that we know if all these kind of the new ideas or new solutions can work or not.
You mean the label, how to evaluate
Yes,
these
yes.
methods, right?
Know if this technology is mature or not.
Yeah. I think it's only through when you only run on the customer's sites or manufacturing sites, can you know whether this method is working or not? Yeah. Because this data is proprietary, so they cannot share with us directly, so we can evaluate at our site. But we cannot evaluate on our site. So So these methods can only be evaluated on the machines that in the customer's fabs. Yeah.
I see. And yeah, thank you.
How do you keep ground truth? You say, this reticle has a defect. We know whether it's truly a defect or not.
Yeah, that's a good question. So after we report the defects on the reticles, the customer will use another machine that go through each defect region, and that machine has a way higher resolution to see exactly what's going on. But the problem is that you cannot use that high resolution machine to check every detail of the reticle. Yeah.
Because
it's too slow.
Okay.
Yeah. Right. I think I can stop earlier, I guess.
Yeah, if there is no more questions, we can wrap here early. And yeah, feel free to talk with Joey if you have any interesting to know about like KLA or what kind of the things they're doing following this. Yeah. Thank you, Joey.
All right, thank you.